Have you ever noticed how roads in cities are often perpendicular to each other? Or how lines of latitudes and longitudes on a globe intersect each other at a perfect 90 degrees? There's a beautiful piece of mathematics behind this concept, and it is known as orthogonal trajectories. In this video, we explore what are orthogonal trajectories, why they matter, and how to actually find them step by step. Let's start simple. Imagine you have a family of concentric circles centered at the origin. Now, ask yourself, is there another family of curves which intersects each and every one of these concentric circles at a perfect 90 degrees? Yes, you're right. It is a family of lines which passes through the origin. At its core, orthogonal trajectories are about finding a new family of curves that are perpendicular everywhere to a given family of curves. As students of mathematics, we know that the slope of a given curve at a point is given by its derivative, dy by dx. We also know that for two lines to be perpendicular, the product of their slopes must be equal to -1. This means that the slope of a given line is equal to the negative reciprocal of the slope of the other line. So say that the slope of a given family of curves m1 is equal to dx by dy. This means that the slope of its orthogonal trajectory is given by minus dy by dx. This is the essence of the concept of orthogonal trajectories. Let's talk about the historical context of orthogonal trajectories. While it may sound modern, it actually dates back to over 300 years. In the early 1700s, the Bernoulli brothers and Leibniz had a pertinent question. If you have a given family of curves, can you find another family of curves which intersects each and every one of these at a right angle? That was the simple problem of orthogonal trajectories. And this became the very essence of physics, explaining heat flow, electrical fields, and even planetary motions. So this simple problem of geometry is the dawn of calculus itself.
Hello guys, let's explore the math behind orthogonal trajectories. For the first example, let's take an equation of a family of curves x squared plus y squared equal to c. The first step is to differentiate the equation in terms of x. So we get 2x plus 2y dy by dx equal to 0. Taking it to the other side, we get 2x equal to minus 2y dy by dx. We cancel out the 2's and we get minus x by y equal to dy by dx. Now, as mentioned earlier, to find the perpendicular orthogonal trajectory, we replace dy by dx with minus dx by dy. So replacing that, we get minus dx by dy equal to minus x by y. The minus cancels out. We get dx by x equal to dy by y. Integrating both sides, we get natural log of x equal to natural log of y plus natural log of c. Taking it to this side, we get natural log of x by y equal to log of c. Log cancels out and we get the equation x equal to cy, which can also be written as y equal to cx. This is the answer to this current question. Let's do one more example of orthogonal trajectory. This is a parabola with an equation y squared equal to 4ax. Differentiating this in terms of x gives us 2y dy by dx equal to 4a. dy by dx equal to 2a by y. As you can see, a is a constant and we need to replace it in terms of x and y. So you get that a equal to y square by 4x. Substituting this in this equation, we get dy by dx equal to 2y square by 4xy. The y cancels out. We get dy by dx equal to y by 2x. Now, as we know, we replace dy by dx by minus dx by dy to find its orthogonal trajectories. So minus dx by dy equal to y by 2x. Minus 2x dx equal to y dy. Now integrating both sides, we get minus 2x square by 2 equal to y square by 2 plus c. The 2 and 2 cancels out and we get y square by 2 plus x square equal to c. So as you can see, the orthogonal trajectories of parabolas gives us an ellipse. Let's understand what the self-orthogonal trajectory is. A self-orthogonal trajectory is a one-parameter family of curve with a unique property that any two distinct curves from the same family intersect at a right angle. In simpler terms, if we pick two curves from the same family of curve, they should intersect at a 90-degree angle. Let's see this family of curve. It's y square equal to 4 into x plus c and y square equal to minus 4 into x minus c. They are self-orthogonal and they belong to the same family of curve. Samarth will explain a problem and help you understand this better.
Let's take an example to understand better. Prove that the given family of curves y square is equal to 4a into x plus a is self-orthogonal. We differentiate this with respect to x and we get 2y dy by dx is equal to 4a. Since there is a constant, we write it in terms of x and y. We get a is equal to y by 2 into dy by dx. This is taken as equation 2. Substitute this into 1, we get y square is equal to 2y dy by dx into x plus y by 2 dy by dx. Simplifying it, we arrive at equation 3. To prove orthogonality, we know that we substitute dy by dx as minus dx by dy. So substituting it into 3, we arrive at this. Y square is equal to 2xy into minus dx by dy plus y square into minus dx by dy the whole square. Simplifying it further, we arrive at 4. Y square is equal to 2xy into dy by dx plus y square into dy by dx the whole square. Here we see that equation 3 and equation 4 are similar. This proves that the given family of curves y square is equal to 4a into x plus a is self-orthogonal. Now let's step out of pure math for a second and explore where orthogonal trajectories actually show up in the real world. One classic example comes from physics. Think about equipotential surfaces and electric field lines. Wherever there's an electric charge, electric field lines spread outward and equipotential surfaces wrap around it. These two sets of curves meet at right angles, a perfect example of orthogonal trajectories. Another place is geography. Let's take a globe. On a globe, longitude lines run from pole to pole, while latitude lines wrap around horizontally. Wherever they meet, the angle is 90 degrees. That's orthogonal trajectories for you, hidden in plain sight. And here's another one, fluid dynamics. Streamlines of flow and pressure line often intersect each other at 90 degrees. This helps engineers model how fluid moves efficiently around objects like airplane wings. And in engineering, heat flow gives another example. Heat naturally moves perpendicular to temperature contours, so the flow lines and contour lines form orthogonal trajectories too. Orthogonal trajectories aren't just a neat metric. They're a powerful tool that show up when you have two related systems, one cutting across the other at 90 degrees.
Samarth, can you explain what we learned today?
We learned what orthogonal trajectories are and how to solve them. An orthogonal trajectory is a curve that cuts every member of a given family of curve at 90 degrees. We also learned what self-orthogonal trajectories are and covered the applications of orthogonal trajectories in a real-world context.
So we have a 3-step recipe of how to solve this orthogonal trajectories. Step 1, we differentiate the family of curves. Step 2, we flip the slope using the perpendicular condition. And step 3, we solve the new differential equation. Do that and you have found your orthogonal trajectories.
It's a simple idea, but it connects beautifully to how patterns in mathematics describe patterns in the real world. Thanks for watching this video. And remember, the next time you see two lines cross at right angles, there might just be some differential equations at play behind the scenes.